Hi, welcome back to Physics 2. We're going to continue on Chapter 16. And so what we have talked about so far is that charge is a property of matter, just like mass. And what we saw in some of the diagrams is that objects that have a charge, whether it's a positive charge or a negative charge, when they're close to other charges, they each feel a force due to the other. So this force is called the Coulomb force, and it's also called the electric force. Coulomb's law describes quantitatively this force between charged objects. So, a couple hundred years ago when they were doing these measurements, what they found was that when you have two charges near each other, okay, let me get my pointer, there it is. When we have two charges placed a distance r next to each other, okay, we found that the force was proportional to the magnitude of each charge. And so that the larger the magnitude of the charges, the larger the force. It was also observed that the force depended inversely on distance, okay, meaning the farther apart the charges, I think it's written here, the closer the charges, the larger the force, or the farther apart they are, the weaker the force, right? That's an inverse proportional relationship. And so Coulomb's law basically states the quantitative portions. Okay.
I gotta go pee.
Okay, thank you for letting us and the whole class know. That was my son, and he wanted everyone to know what he's going to do. So you guys are all going to be health professionals, so you'll be very, you'll be hearing stuff like that a lot, I'm sure, in your future. Well, maybe not everyone, but I would say a good 80% of you guys. So Coulomb's law, right, describes that proportionality with the charges and inversely proportionality with the distance between the charges. And there's a proportionality constant in order to turn the units of charge times charge over distance squared into a force. And that constant of proportionality is called Coulomb's law, given by the letter K. The value is 8.99 times 10 to the 9 newtons times meters squared over coulombs. So if you analyze those units there, right, if you put that K right here next to the magnitude of the two charges divided by an inverse square law, right, inversely proportional to the distance squared, you can see that that's going to convert the 2 coulombs squared over meters squared into newtons. Okay, so here is Coulomb's law right here. So let me just write it, I'll write it just a little bit cleaner, right? Q over R squared, where Q1 and Q2 are the two charges, okay? The value of their charge. R is the distance between them, and so we need to use SI units, right? Coulombs for the charges. And meters for the distance. So this gives us the magnitude of the charge. So that's why you see these bars here. These are magnitude bars, okay? So they're letting you know that if there's a negative sign, so if one of those charges is negative, we're going to ignore the negative sign, okay? Because this is giving us the magnitude of the charge. And so, well, how do we account for the negativeness, right? If one of the charges are negative and one's positive, well, that's going to change the direction of the force. So instead of including the negative sign in the magnitude, we're going to let the negative sign tell us the direction of the force, okay? And so the direction of the force that one charge feels due to the other is going to be given by a simple rule, okay? If the signs of the charges are positive, then the force is going to be pointing directly away from the other charge. If the signs of the charges are opposite, so if one's positive and one's negative, then the direction of the force is going to point directly toward the other charge, okay? So that's basically what this shows you here, right? So these are the two cases. So you can see that for this charge, the direction of the force, since this one is positive, it's going to point directly away from the other charge, okay? So what does directly away mean? All right, directly away is a very important word. Directly away, or directly toward, as in this case. And so let me describe what I mean by that. Okay, straight line path. All right, so you connect the two charges with a straight line, and then that force vector will follow that line. Okay, it'll be along that line, directly away. Now, if the charges are opposite, well, you draw that line between the two, and you can see that the force vector will be a straight line path directly toward the other one. Okay, so that's how you know the direction. I mean, here, looking at this picture, it's like, duh, because they're you know, on a horizontal line. But, for example, what if I have them at an angle? Okay, what would be the direction? Well, I draw my straight line path, okay? And I don't know, well, I'm going to find out if it's positive or negative, right? So one's positive, one's negative. I believe they like to use red for negative. So this is negative, this is positive. And so they're going to be attracted to each other. So the force that the positive charge feels is going to point directly towards the negative charge, and the force the negative charge feels is going to point directly towards the positive, okay? So draw that straight line path connecting the two, and then you're either going to draw a force arrow directly toward or directly away, depending on if the charges are positive or negative. And so that's the direction of the force, right? Coulomb's law gives us the magnitude, and then the direction we get from using this simple rule, okay? Whether the charges are positive or I'm sorry, whether the charges are alike or opposite charges. So what you'll notice is when we calculate the magnitude of the force, it doesn't matter which we call Q1 and which one we call Q2, right? Because of the property, the commutative property of multiplication, you can certainly multiply Q2 first, right? In other words, what I'm saying is that Q1, Q2 is equal to Q2, Q1. And so that property, that math property, is actually a physics property as well. And that's Newton's third law. So Newton's third law tells us that the force that one charge exerts on the other is in equal magnitude but opposite direction as the force that the other charge exerts on the first one, okay? And you can see that mathematically, and then there's also a physical explanation as well. So we're going to do some examples. I have these already posted on Canvas. So if you go in modules, these are called PCAST. Okay, these videos are called PCAST videos, and then the title of the video is the example. So it doesn't say example 16.2, it says PCAST, calculating electric force. Okay, so I want you to do that one, and you can watch the video, and these slides have them all fully explained. Okay, and I want you to do that for 16.2 and 16.3. And then the next example, 16.4, is also, all three of these are in modules, in chapter 16 modules. So 16.4 is very important. So I want to just tell you what aspect to think about in terms of, what could show up on an exam, okay? So 16.4 is really going to bring out the vector nature of these types of force problems, okay? And so let me just give you a brief outline. So in this problem, if you read through the problem, it says that there's three charges and they're arranged in a triangle. All right, it's not directly stated they're in a triangle, but if you read through how they describe the location, it ends up being a triangle like this, okay? Where you have, remember, blue is positive charges, so you have a positive charge here at the top of the triangle, positive charge, and then a negative charge over here. And so I want you to quantitatively go through this problem and find these force vectors, okay? Find the x component, find the y component of each one, add them up, okay? And, but what I want to talk to you about in terms of how this could show up on an exam, because obviously numerically working through this problem is very long, right? Look, there's a lot of algebra here. There's a lot of trigonometry. It's really not that bad once you have the procedure down, okay? So I don't want you to worry about it like too much, but what I want to show you is how in an exam I might take something that's a very long problem and turn it into an exam problem. And so the way I would do that is you can actually answer this question without doing any math, okay? You can actually answer it just by looking at the vectors. And so let me just read what the question is. So the question is, calculate the magnitude and direction of the force on Q3 due to Q1 and Q2. Okay, so Q3 is at the top. So Q3 is at the top of this triangle. And then we want to find the force that Q1 exerts on Q3 and the force that Q2 exerts on Q3, okay? And we want to add those force vectors up to find the total force. And so the way that this could show up on a exam is I could ask which direction, so maybe I would give you some, which direction would, let's say A, B, C, D, what direction would that total force on Q3 point? Right? The force that Q3 feels due to Q1 and the force that Q3 feels due to Q2. What direction would that point? So what you would do is you would say, okay, well, I can see that Q1 is positive, Q2 is positive, so its force vector is going to be a straight line path, right? Straight line path directly away from the other charge. However, Q2 is negative, Q3 is positive, so the force vector is going to be a straight line path directly toward the other charge. And so these two red vectors, when they're added together, they're going to add to a vector pointing to the right. Why? Because the y components of each force vector are going to cancel. They're equal in magnitude, opposite direction. And then the x components are going to add together. So your total would be a vector pointing to the right. Okay, so that's the way that you should learn how to master this problem in all the examples, because even though they're quite long and they wouldn't word for word appear on an exam, there is a conceptual question that I could ask about it. So now look at this one. So in this one, you have the three charges lined up on one axis, okay? And I believe this problem asks you to find, express one charge in terms of another. But the way I could look at this problem and ask a question that would be a good test question that would take less than 5 minutes to complete would be, what would be the net force direction on any one of these? Okay, so let's just get rid of this. Let's just do that. What would be the net force? Let's look at this top guy right here. So what direction, so net force direction on Q1. And then let's assume that they're all the same charge. Okay, so let's assume Q1 equals Q2 equals Q3. And so let's just draw our force vectors, okay? I'm gonna draw them in purple. So if this is, so what is the force direction that, this is Q2 and this is, this is Q2, Q3. We'll call that Q3 and this one Q2. So what's the direction that, what force direction does Q3 exert on Q1? Well, it looks like they are opposite, right? And so they're going to be attracted to each other. And since I'm talking about Q1, I'm going to draw my force vector on Q1 and it's going to go straight towards Q3, okay? So that's going to be F3 on 1. So now what about Q2? What effect does Q2 have on Q1? Well, they're opposite charges, okay? I'm sorry, they're not opposite. They're both blue. They're the same sign charges. And so Q1 is going to want to move directly away from Q2, right? So F2 on 1 will be to the left. And so the question is, what is going to be the net force direction, right? We have one force pointing to the right, F31, one force pointing to the left, F21, which is gonna, which is the most positive and which is the most negative? Well, that's when you examine the magnitude of the force, okay? So the magnitude of the force, F31, well, Q3 and Q1 are really close to each other, right? They're only off by a distance d. So if they're the same charge, my Q's are squared, and they're a distance d apart, okay? Now let's look at there's my force. Let's look at F21. KQ squared, numerator's the same. They're all charge Q. What about the distance? Well, this one's farther away. So that force value is automatically going to be 1/4 smaller, right? Because we square the distance. So KQ squared over 4D squared. So obviously F31 is going to be bigger. It's going to be the most dominant force. And so then the net force would be pointing to the right, the same direction as F31 because it's larger in magnitude. Okay? So that's a way that, you complete this question here, this example, and you understand the concepts going on. And although it's asking a slightly different question, that's how I could look at this and turn this into a test question, okay? In the question, you can see it's asking for something totally different. It's asking you to relate Q in terms of big Q, okay, which is fine. But in order to answer that question, you have to understand the concept that I just laid out here in this example, in this, test example. Okay, so complete those examples, do the math behind it, okay, churn through it. This is going to help you with resolving components of vectors, which you need to do for example 16.4. Okay, and so this is just a snippet from chapter 3 that reminds you of how to find the components of a vector depending on what direction that vector is pointing, okay? And so then I kind of slid that into the middle of example 16.4. So if you do follow the example in the slides, this is coming up at the right spot. Okay, so the video also will talk about these steps here. And let's now, so now assuming that you have, stopped this video and have done those 3 examples, let's come back to the slides and let's do this conceptual problem. So in example 16.2, we had a drop of water, right? And from that drop of water, we said that we removed, so let's recall, right? The drop of water has a bunch of molecules of oxygen, 2 hydrogens, right? And there are 10 total electrons for each molecule, right? 1 for each hydrogen, 8 for oxygen, right? 8 in oxygen, and then 2, 1 for hydrogen, another 1 for hydrogen, okay? And so in that problem, what we did is we said, we separated the electrons from the protons. So essentially what we did is we created 2 balls of charge, where one ball of charge had, I forget the number. It was a very large number of molecules. And so therefore it would have 10 protons times whatever number of molecules there was in there. Okay, and then in this side we had 10 electrons times however many number of molecules was in there. And what happened was, I'm reviewing example 16.2. I believe now, if I remember correctly, we had 224 coulombs of charge, well, negative, right, because these were the electrons, in one drop, and then we had positive 224 coulombs of charge in the proton drop. And so this is the result of example 16.2. What this conceptual question wants to know: if instead we removed only half of the electrons from the water, and then move them to the same distance. Oh, what was the distance? I believe it was 10 centimeters. Okay, which is 0.10 meters. How would the force compare? Okay, so force in example 16.2 was K, 224 coulombs squared, right? Because we're getting the magnitude here, so I'm just multiplying 224 times 224. And then the distance was 0.1 meters squared. And now in the force in this example, we're going to compare the two. Okay, so now if we only remove half the electrons, how much charge do we have in each drop? Okay, so I'm going to take half the electrons out. So now instead of minus 224, I'm going to have a little bit less negative charge. It's going to be half of that, which is 112. And so now over here, we had plus 224, but now we're removing half of the electrons. And so the total we're going to have here now is positive 112. Okay? And so now the force we're going to calculate here is going to be 112 coulombs squared. And, well, that's half of this guy, right? So I can rewrite this as our old number squared. And then I can pull that 1/4 out. And I can see that our force is 1/4 as great as in the example 16.2. So it should be 1/4 as great. Okay. Yeah, and that's the correct answer. I mean, so, okay, let's like kind of like zoom out a little bit. Like what's going on here? Reading comprehension is the underlying kind of problem here, right? I feel like if I just told you, hey, how does the force compare between two charges of 224 versus two charges of 112, you'd be like, oh, well, hello, 1/4 is great, right? But the question didn't ask you that way. It asked you in kind of a way that tests your reading comprehension ability. And reading comprehension is so essential. I mean, not just for your guys' majors, okay, in biomedical sciences and healthcare, okay, but any major, all right? So reading comprehension is very important, and that is the really I would say, the most difficult part. I feel like you guys probably mathematically can handle this very easily. The reading comprehension and kind of pulling out what we need to solve the problem out of all this whole paragraph is probably arguably the more difficult aspect. So just think about that, okay? If you look at this and are confused, I doubt it's the math. It's probably the reading comprehension part. And the only way to be more successful in that is to practice your reading comprehension and just read more, okay? Less time on TikTok, more reading. Okay, I'm not accusing you guys of being on TikTok too much. I'm just being an old fart, all right? That's my old fart advice. All right, so let's recap. So we talked about Coulomb's law. Coulomb's law, F, K, Q, Q, okay? However you want to differentiate the two Qs, whether you call it Q1, Q2, QA, QB, whatever, over distance between them squared, okay? Here's a picture of this equation. All right? That gives you the magnitude of the force. How do we find the direction? Positive, positive, negative, negative, positive on this side. Okay, here's our 4 cases. All right, opposites, same sign, repulsive force. Same sign, repulsive force. Straight line path directly away, straight line path directly away. Opposite signs attract, right? Opposites attract. It's like an old song from the 1980s, Paula Abdul. Okay, opposites attract, straight line path directly toward the other. Okay, this gives you the direction of the force. This gives you the magnitude of the force. Okay, so that's section 16.4. I'm going to stop this video and post another video starting we're still in chapter 16, but we're kind of starting a slightly different idea. Okay? Do those examples that are on Canvas. Follow the videos or do them yourself.